Welcome to the final session of the day. I hope you enjoyed the keynotes. Hope to also see you tonight at the museum. So just a reminder, the buses leave at 6:15. Please join me in welcoming our next speaker, Jakub Szafranowicz.
Welcome, everybody. I hope you're enjoying the conference so far. I'm with AWS, Amazon Web Services. I'm sure you've heard of us. I'm a security researcher, and the focus of my research is on open source software. And specifically, we look for vulnerabilities and we fix vulnerabilities in open source software in collaboration with the open source projects. Why am I here talking about zip files? So I'm going to ask you a question. How many people here do not have a smartphone? Anyone? If you have a smartphone, you got a zip parser in your phone. Both Android and iOS use zip files to package the applications. If you got a smartwatch, you got another zip parser. Now, if you take a moment and look in your wallet, if you have a debit card or a credit card that's got a chip on it, congratulations, you got another zip parser. Most EMV chips, which are on credit cards, are built in Java card, and they have zip parsers. The presentation behind me is made using PowerPoint. Modern PowerPoint formats, which is Office OpenXML, are zip-based as well. 3 zip parsers built by 3 different companies, so 3 different projects. And all 3 of them could be vulnerable to the attacks I'm going to talk about. But the other reason why I'm fascinated by zip files, besides the fact that they're literally everywhere, is also because the format is very complex. It's also how it has grown organically over time. And all of the things that got bolted onto it, it's a very interesting format to research and to attack. Now, there's a lot of things we can talk about, but the presentation is only a certain number of minutes. What I'm going to talk about is basically, we're going to start off by talking about the zip format itself. Then I'm going to talk about all the various different ways you can attack zip. I roughly separate that into four areas: hiding data, denial of service, file system manipulation, remote code execution. Towards the end, I'm going to give you a couple examples of how you create your own zip file, how you create a zip bomb, don't send it to your friends. And we're also going to talk about some recommendations and takeaways. One thing also to add, all of the research that I'm discussing is not original research. Some of the stuff has been known for over 25 years. And what I'm really here to, the value I'm bringing here is that I want to kind of collect all of it and present how all of it kind of flows from the format. It's not that each attack on zip is independent. Most of them, if not all of them, derive from the format itself. Now, let's talk about zip itself. Now, this is the structure of a zip file. So, first of all, zip is very old. Zip was created in 1989. It was created by a person named Phil Katz, and then he created a company called PKware, Phil Katz, PK, which created a product called PK Zip. And most of the signatures inside zip actually use its initials. If you start reading the file from the left, those are the blue entries on the left, everything is more or less similar to other formats. You got a separate entry for each file in the zip. It's got some metadata, it's got a compressed file. Where things become interesting is once you go to the second one. The second one, which is the purple section, is known as the central directory. The first one is known as local headers, then you got the central directory. The central directory has exactly the same thing. It's got copies of all of the metadata from the files themselves without the actual file content. And then the third piece, which is all the way in the end, is known as the end of the central directory record. That simply contains a pointer to the central directory. Now, what that means is this is a logical structure that gets overlaid over the physical file. But what means is that you read the file backwards. Instead of starting from the beginning and going forward, you start from the end. You parse that record. It tells you where the central directory begins. And in the central directory, there's a separate file entry for each file, which then tells you where the file entry itself is located. Now, most implementations that I have looked at read the file the way it's described here. Some do not, and they use what's known as streaming mode, where they essentially only read the beginning of the file and they stop at the purple point. They don't go past that. Now, the question you may ask is, who in the world would come up with something like this? Now, the reason for this is because keep in mind how old zip is. Zip is 1989, so think floppy disks. If you want to quickly modify the content of a zip archive that's split over multiple disks, you would modify the central directory that's located in the end. This way you don't have to go back and modify the original floppy disks. And another thing that comes out of this also is that because the technology is so old, there are constraints of how big a zip file can be, because it's only 2-byte fields, for example. There are constraints about, there's bit flags. There's all kinds of things in there which do not make sense in, essentially, if you were to design a JSON format or XML format, you wouldn't design it this way. Now, the other thing is the metadata in a local header is limited because it was never designed to be used. Why is it there in the first place? Besides the ability to modify the file, what happens if your floppy disk gets corrupted? So you got 10 floppy disks, your last one is corrupted, that has a central directory. You can now read each of the first 9 disks and recover your data. So that's why the data is there, but the data is limited because it's only meant for that one purpose. Now, most implementations do use the central directory, but there's another aspect that was also very interesting, MIME sniffing. And MIME sniffing is an approach that a lot of applications use. They essentially look at the magic value at the beginning of the file, say, this is a GIF file, this is a PNG file. However, in zip, you can't do that, because if you sniff the beginning of the file, you end up just looking at the local header. It doesn't tell you whether that's really a zip file or not. In terms of compatibility, zip supports every operating system there is. Because it supports every operating system there is, it can store things in very strange ways. So there's kind of a normalization process that happens, both for different file systems and for Unicode. How you get from the file the file name that's contained in a zip, and how you essentially normalize that into the file system and back. And that's one of the areas where attacks are possible. You could have duplicate entries in zip, which is strange. Why would you have a file format that represents a file system that has more than one entry? But that is allowed. A name can be empty. You could have a zip entry that has no name. According to the official documentation, it's to support files that are being run from standard input. But I never really found a good answer. You could have directories. You could have symbolic links. You could have attributes and permissions. Permissions are your standard Linux permissions, but you could also have Windows permissions, you could have macOS permissions, and the implementations are different for every operating system. Another thing that's also possible is what I call attributes. In Windows world, they're called ADS, where you have a separate, essentially, set of metadata that resides next to a file. In macOS and Linux, they're called resource forks. And those can also be stored in zip and can be used for attacks, which I will discuss later. Now, extensibility. One interesting thing that I found, which was surprising to me, zip standard does not exist. There is no zip standard. It simply doesn't exist. And there's an XKCD cartoon about how the whole internet is based on one guy in Nebraska. Well, all of zip is based on a simple text file that's published by a company out of Wisconsin. The company is PKware. Whenever they decide to extend the format, they decide to just change the file. The closest thing that we have to a standard is an ISO standard. It's called ISO 21320. But it's not a standard. It's really what they call a profile, where it basically says, take the app note, which is a text file, at version 6.3, take some features out, and there you go. They didn't include a copy of it. Now, the reason why it's set up the way it's set up is because historically, PKzip came with the file. So you get the product, and you get a description of the product. And InfoZip, which is the open source implementation of zip, does the same thing. But that also means that every implementation can do whatever they want. If PKware decides to document the differences between implementations, they will do that. Otherwise, they will not. Original format has limits. Many fields in the original format have 2 bytes for certain values, and that limits how big it can be. So because of those 2 issues, meaning that one company controls it, and different implementations will do different things, and the second is that there's limits, there's extensibility built into the format, but the extensibility creates problems. Zip64 is a second set of fields that overlay the main set of fields that essentially use bigger values. Instead of having 2 bytes, you could use 4 bytes. I think it's 4 or 6 bytes. You get bigger zip files. If you have an implementation that doesn't support it, you're out of luck. Extensible fields, when you have file entries, you could have, in each of those fields, you could have metadata. And those metadata can be defined by anyone. There's no centralized control until pkware decides to incorporate it back into the app node if they do. And you could essentially add additional metadata on top of your file entry. New compression methods, one of the things that implementations tend to do is deflate is the classical zip compression. How about MP3? How about JPEG? How about PP WavePack? WinZip has implemented those special compression methods directly built into their product. That means that the MP3 file compressed through WinZip will have an MP3 data stream directly embedded. Now, in terms of security issues, so there's 4 sets of security issues that I roughly divided them. They tend to overlap between one and the other. And I really organized them from a point of view of an attacker. So from a point of view of an attacker, the first one would be hiding data, which is steganography. Now, this one is an interesting one because it really does not matter for most people. Like most people who use Windows, Mac, or whatever, if you hide something in your zip file, nobody really cares because you need a way to extract it out. It becomes very, very important for email gateways, security products, DLP systems. Any system that's seeking to prevent data from exiting an organization, or you're looking for data not to come into an organization, whether it's malware or anything else, this becomes very important that you don't use zip. The attacker should not be able to use zip as a way to carry the data in or carry the data out. One interesting thing about this particular set of attacks is that security tools tend to analyze zip files very differently than end users. And therefore, a lot of these attacks, you end up having a zip file that will pass through the email gateway, but you double click on Windows or Mac, it will open up the payload. Because the implementation that you're using for end users is not the same. Because security tools very often will use a different parser, or they will have different requirements. Now, there's 2 different places you can hide data. You can hide data inside a zip entry, or you can hide data inside the zip structure. Now, like I mentioned earlier, there's a whole bunch of features you can do. That you could have custom compression methods. You could have weird metadata sizes. And if you put in features that someone does not support, the security product that you're using might just simply let the thing go through. It may analyze the rest of the file, but that particular data entry may maybe get skipped. So you could have a file that will get analyzed, 10 files, 1 file gets skipped. It could be something like zip64, which you don't support. It could be an extra data field, which is not supported by them. It could be as simple as a file size. File size set to 0, it will pass through because the implementation thinks there is no data. It could be an invalid checksum. It could be the MP3 method that I mentioned earlier. It could be 2 different entries. So all of those things can fail analysis. Another interesting thing about entries without content. What's the directory? If you store a directory, the directory has no content. It's empty. It's a directory. You put files into a directory. The zip specification does not give restrictions on that particular point. You could have a directory entry with content in it. You could have a symbolic link with 2 different sets of content on it, depending on how it's implemented. All of those things can carry data. You could also have comments. And comments are something that a normal person would not see. Some implementation will show to them, some will not. But security tools may sometimes ignore comments. The other way you could hide data is you could hide data in the zip file itself. Now, as we mentioned earlier, the zip file has these 3 areas. You have the central directory, you have the local headers, and you have the end of the central directory record. They're all malleable. You could stick data anywhere in between. You could put data before the file, you could put data after the file. You could put data between 2 entries, you could put data between the central directory and the local entries. Basically, you could put anything you want in there. If an implementation is not checking for that extra data, they will not find it. Another thing also is you could have a difference in headers. You could have a central directory header that will tell you A. You could have a local directory the header will tell you B. They will mismatch. If implementation doesn't know the format or is not careful, it will go through. The nested zips. Nested zips is also an interesting thing that's for this particular set of attacks. When you nest a zip and you deliver it to an end user, they have to double-click into it and into it and into it and go all the way through. But a security tool has a requirement where they want those nested files to be analyzed. The problem you run into is essentially if you go too deeply in, you end up with recursion, and the tool will crash. If you don't go deep enough, then you will analyze everything that's in there. And in theory, an end user will be able to click all the way through, or you could hide data in there. So a lot of security tools have a trade-off where they have a limit past which, let's say, 25 nested files. They will not go past that point. The interesting thing is what happens when they get triggers. Do they silently let the file go through, or do they flag it somehow? And the behavior is not consistent. So for each of these categories, I'm going to give you a couple examples from the real world. And if you look at the dates, these things are not new. The first one there is a vulnerability node from CERT. You set the file size to 0, multiple antivirus products let it go through. Second one, the version field is greater than 15. That means that the specification that PKWare provides has versions in it. You set version 100, it goes through. GFAR, and the one lower down, which is glue is when you append one file to another. GFAR is an old Java vulnerability. It looks like a GIF because it sniffs like a GIF, because the beginning of it is a GIF. But if you read it properly backwards, as Java would do, it's an executable applet. Glue is a similar vulnerability in Microsoft, which is a lot more recent. You have an executable file that is digitally signed with Authenticode. It will pass authentication. In the end of that file, you append a jar. And again, you end up with a kind of a polyglot where Microsoft thinks the file is perfectly fine. But if you run it with Java or any other system that runs executable code through zip, it will execute. And it will just go through. Mac OS is an interesting one also, where you could stuff data into it, where Gatekeeper will bypass Gatekeeper. And there's a whole bunch of other ones, essentially, when you mess around with different parts of a zip file. And at that point, they will go through. Now, this first category is interesting, but it's only applicable for a subset of people. The second category is denial of service. Now, denial of service is basically you crash the thing, or you make it run out of memory. Most of these are essentially used for laughs. They're a very common technique if you're doing a capture the flag competition. But some of them can be fairly dangerous, because if you have a security appliance that crashes, what happens then? Or if you have a process that does not set up correctly to recover, what happens then? Now, for denial of service, most of them are basically somewhat similar. You got the most famous one is what's known as a zip bomb. A zip bomb is very simple. You take an empty file, you can compress it very, very efficiently. You send it to someone, it decompresses, you got a zip bomb. But some of the other denial of service attacks are a lot more subtle than that. The core issue with a zip bomb is not the zip bomb itself. It's the fact that a zip implementation, when it's extracting data, it doesn't have any limits. It doesn't look at how much memory or how much disk is being consumed until it completely runs out of it. Or if it's using some sort of recursion, it doesn't have a limit on recursion. So some implementations don't have limits. Another thing that happens is, let's say you have an entry in the zip that says there's 100 files within the zip file. Then the implementation goes ahead and pre-allocates memory for efficiency purposes to decompress 100 entries. 100 is fine. Try 10 billion. Again, no limits, because they are pre-allocating memory or disk space based on unvalidated data from a file they don't trust. Unexpected values is another one. When the specification is complex, and there are things that are technically valid but are not, but there are things that are for sure invalid. A lot of them, the particular implementation may not account for because they've never encountered it. A lot of these implementations, the problem is that they don't bother reading the spec, the closest thing we have to a spec. And the implementation is not necessarily consistent with what's expected. And then usually what happens is it crashes. The last one is overlapping and nesting. As said all the way in the beginning, the logical structure of a zip file is that you have the central directory that points to local headers. You could have 100 central directory entries pointing to the same file. So you have your zip bomb, you stick it into your file, and then you construct the zip file in a way where there's 1 million of central entries pointing to the exact same local entry, same exact file. That's an overlapping nesting attack. Now, 2 examples. That one's pretty famous. You could Google 42.zip. Again, don't send it to your friends. That one's more, it's really nesting. It's nesting with a nesting with a nesting. The one on the right, which is made by David Feifeld, is a paper that he submitted to Usenex. He also has it online. That one uses the overlapping thing that I just mentioned earlier, but also uses a lot more tricks than I mentioned about how deflation is done, where an entry starts, where an entry ends. Now, in terms of real attacks, and again, make a note of the years. This attack, the one on top, is 23 years old. Very simple, long file name. Why? How long is a file name on Windows? How long is a file name on Linux? I bet you it's not 65,000 characters in some systems. Zip allows 65,000 characters because of a 2-byte field. ClamAV, the second CVE, you mess with the headers, the thing crashes. Windows Explorer, again, do something unusual values in the zip, it will crash. And the same thing, with many of them, something that's not supposed to happen will crash. Now, I do want to call out the third one from the bottom. This one is one of my favorite ones. Windows NTFS has a bug that if you set a specific ADS attribute 113, the next time you reboot the system, the NTFS partition will delete itself. Because Windows now thinks that that partition is no longer valid. The payload mechanism, this is not a zip bug. Where does zip come in? If zip can carry attributes, NTFS attributes in zip, if you take a zip file, set attribute 113, and then send it to your friend, and they decompress it onto an NTFS partition, the next time they reboot, the NTFS partition is gone. The bug has been fixed. But you could look up the CVE. It's pretty interesting. Now, this third class of attacks is what I call file system manipulation. So again, I'm talking about kind of an order of escalation. Denial of service, you crash someone's system, as long as it's not in their NTFS system, they're going to reboot and go on with their day. This becomes a lot more dangerous. Now, file names in zip don't have restrictions. They have some restrictions. For example, you can't start with a / indicating an absolute directory. If you do, some implementation will parse it anyway. Device letters are restricted. Other than that, there's no restrictions. I mean, you can use backward slashes. But what becomes interesting is, for example, so directory entry uses a /. There's two different ways to implement directories. Most implementations look for the / and then of the file name. But there's a special field with a special bit that can also indicate a directory. So you could attack the difference between two implementations very subtly. Most do not, but one implementation does it this way, one implementation does it that way. So you could send someone a zip file with a directory. It's not a directory name, it doesn't have a /. It'll extract with that special field, it'll become a directory. Symbolic links are supported, two different ways, depending on the implementation you're using. File names are not always validated, and really the two last points are the root of the problem. Is when you're extracting a file, you need to validate to where it's being extracted, but it's not sufficient to do validation. Most programming languages or implementations, the way people implement this check is they do a text check. The way to properly do this is, for example, Java has an API that you could give it a file name, and it will tell you, it will translate the file name into the file system, and it will tell you, is this file located within this directory? And what it does is, it doesn't do text validation. It drops into the OS, and actually it calls the APIs directly in the operating system to tell you whether they're essentially in the right place. Most people don't do that. Most implementations don't do that. And what's going to happen? The file will end up where you don't expect it to end up. Now, I forgot to mention that it's called ZipSlip, but ZipSlip is a marketing name made by SNCC in 2018. The bug is 25 years old. The other thing is what else you can do. So again, you're trying to manipulate the file system. You can manipulate the file location. That was the one we just discussed. Here, you're not manipulating the file location. You want to manipulate the properties of the file. Like I said earlier, zip can store attributes and permissions. They can be in both local central headers. You could set the permissions. You could elevate privileges. You could change the file extension if you put different names in different places. So a TXT file can become an exe file. You could bypass OS security features like the mark of the web on Windows or the gatekeeper on Mac OS. And I'm giving an example of that in a minute. You could change file content. And the third way, again, file location, file properties, file content. How do you change file content? You could have phantom entries. And a phantom entry is that you have an entry that appears in one of the areas in the zip, but not the other. And as a result, depending on how the implementation is extracting, it may be extracted, it may not be extracted. You could have two different entries referring to two different pieces of data. Depending on how you extract it, different content comes out. You could have duplicate content. Again, like I said earlier, you could have two entries with the same name. What happens when the second one gets extracted? It may override the first. You could have encoding issues. The Unicode and normalization that happens when you translate the file name in zip into the OS name, you can manipulate the name. And then if you can manipulate the name can change. And depending on how kind of the interplay between the two sections, you can actually have a different file being extracted in the same name. Now, some examples here. 2001, like I said, it's much, much older. Absolute file names, an infozip, that's the first CV. The second one, you have invalid characters between the dot characters, it's a null. When it gets normalized into the file system, character gets deleted, and then you have dot dot, you go up one directory. Third one, which is also infozip, is the privilege escalation. The fourth one is it's showing the user one section, but it's actually extracting something else. Then you got not sanitizing path, you got duplicate manifest names, writing a file outside of the target directory, you got your symlinks. The last one is actually a lot more interesting. Mark of the web is a security feature in Windows where an attribute gets set on a file saying that this file came from the internet, do not execute. Zip can set a file attribute as read-only. Read-only is a fairly common attribute. A file gets extracted, set as read-only. A different component of Windows that sets mark on the web attribute can no longer touch the file because the file is now read-only. And it essentially just bypasses the entire mechanism. The last one is remote code execution. So there are three ways you can get from a zip file to actually execute remote code. One is kind of straightforward. Most implementations need to be optimized. If they're optimized, they probably have denial of service issues because it's probably C code, C++ code, assembly code, whatever. From there, you can actually escalate into memory disclosure if you go past the buffer. You could go to RCE from there. And again, these are typical C, C++ techniques that I'm not going to go into, but I'll give you some examples. One thing to point out is that things that are less common are more suspect. For example, the MP3 thing I mentioned earlier, like if you are running a security gateway that's checking zip files, you don't even know there's an MP3 parser in there. Like, how would you even know, or a JPEG parser? Because it's such a rare piece of functionality. But if the zip implementation you're using supports that, it's going to be in there, and it could be hackable. The second way is patch transversal. So we mentioned earlier that zip slip and other related things. You could change file names, you could change file permission, you could change file locations, you could use symbolic links. Some implementations actually pass the name to shell, so unzip in shell directly. What will happen is files will go somewhere else. They'll go into rc.d folder, they'll go into a startup folder on Windows. If you're using a web server, they'll go somewhere where they can be invoked as a remote shell. The third way is digital signatures. So one is file issues permissions, but also really digital signatures are a lot harder to protect against. We're talking about a system that's expecting executable code, and it's trusting a digital signature to make sure the code cannot be executed. So think like something like Authenticode. In an Android world, most Android applications are digitally signed as well. If you could mess with those digital signatures where the application is going to expect something and is going to trust it once it passes the signature check, then it will execute. The reason for that is because you can't sign a zip archive without manipulating the archive. A lot of implementations just stick a special file in there, or an Android, they put a special block somewhere in the zip file. And once you start manipulating things as opposed to using like a separate PGP signature, then you have a lot of issues, and you could bypass this. Now, here are examples. The first one is basically your garden variety, garden variety buffer issue. You got metadata issues with the Office OpenXML. You got heap memory. Master key is a bypass for Android, where you could bypass the signature scheme. You got arbitrary file writings through the dot dot. Again, this is a remote vulnerability through a web shell. You got symlinks. You got unzip lock. If you're expecting firmware, this is a Huawei vulnerability. And you supply a file that's valid, and it will pass validation, then they're going to end up installing a firmware file that's not really validated. And then you got a PHP web shell, and you got the most recent one was using the North Korean attack a couple of weeks ago. It's in WinRAR, but it's in WinRAR implementation of zip. Now, I'm going to give you 3 examples. This is how you make a zip file. It's very simple. You echo, you zip, and that's a zip file. That's what it looks like. This was done on Mac OS, but it should be fairly similar on Linux. If you parse the zip file, this is what it looks like, sort of a little more color-coded. The yellow portion is the local header. That's the signature for the local header, and that's the one that most people use for MIME sniffing. The second one is the central directory. That's the green one, and the last one is the end of the central directory record. The hello world section there, that's the actual content. And the parsing is done backwards. You go down in the section all the way in the bottom. That tells you to go to the second section. That tells you to go to the first section. Second example is, and actually, this is a good utility called zip details. Zip details will dump out the actual zip file for you. So for example, in this case, you see the local header, you have the version number, and that's what one of the CVs I mentioned earlier. You could set the version number very high. Which operating system it's meant for, the general purpose flag that has like little different bits of values. You got your compression method. That's where the MP3 value would come in, like if you're doing an MP3 compression. You got the CRC checksum, the length files, the file name length. I want to call out the extra length field. That's the extensible fields. The extensibility in zip is done by adding those fields. So that tells you that there's going to be some number of those fields. That's what the fields look like. The extra one number on top of it, that's field ID 5455. That stores a timestamp with greater precision. The second one is the one that's dangerous. That's permissions on Linux. And you could make one up. You make one up, you stick it in there, and implementation won't parse it. And there's a lot more of those than, obviously than these two. And then you got the payload in the bottom. It repeats a second time in the central header. So now you got the same exact metadata that's repeating itself a second time in the central header, with a little bit extra information. The extra information is these 2 fields on top. File attributes, external and internal file attributes, those also impact permissions. And then you got the end of the central directory record. And again, working backwards, you'll start parsing here, it gives you the offset, you go back to the central directory, and then goes to, you go back from there. The last thing is, two more examples. How do you manipulate zip file structures? Very simple example. You create a zip file. You append to it a text file. The zip file is perfectly fine. If you do unzip -L, which lists out, it doesn't see the extra data because unzip, which is infozip, doesn't detect that. But if you run zip details or you do just a tail on it, you'll see the extra text file appended to the zip file. And this last example is, this is how you make a zip bomb. This is on Mac OS, which uses mkfile. I don't remember exactly what the command is on Linux, but something very similar. You create a 1 GB empty file, you compress it, it will compress down to 1 megabyte. If you want to be even more careful, or if you want to shrink it more, you could shrink it down to 1.3 kilobytes by using an option of zip where it's compressing internally with bzip2 algorithm, which is not supported by everyone, but it has a greater compression ratio. Now, I want to close off. Where do we go from here? You need to know the format. If you are a developer who's implementing zip, you need to know what you're doing. And just to paraphrase someone that I saw, a different researcher, it took him probably several weeks to understand it. It's very complicated to just read through the spec over and over and over, and it has all these gotchas, and actually comparing against what implementations are actually doing. You should know who's providing your parsing code. If you have a zip parser, whether it's in your phone, it's in your smart card, it's in your security gateway, where did it come from? And it may come from an open source vendor. It may come from somewhere else. It may be something that, I don't know where it came from, but you need to know where the code is coming from. Resource limits are very important, especially on the extraction side. Validation, and most of these errors are validation errors. In other words, if you validate properly against the format, you won't have most of these issues. The last one is important for security tools. If the file isn't going through because it's password protected, it's got a 0 file length, it's got some other issue in it, fail correctly. Don't let the file through, as opposed to the CVs I mentioned earlier, where the file would actually go through. And the larger issue really is that this is not a zip-specific issue. These type of issues are found in other formats. I mean, I haven't looked at tar, I haven't looked at JZip, but OpenXML, Open Document XML, there's research being done on a lot of these, but there isn't enough awareness and enough research being done on all of these. Any questions, please feel free to send it, but one more thing I just want to kind of add in the end. Actually, it's not, it got missing, it got cut off from the slide. Most of this research, I want to thank, there's a lot of researchers who have spoken on this topic or published on this topic over the last 20 years. I actually have a list of about 20 different references. Yeah, this is the slide I'm talking about. Without these, I could not have come up with, collected this information. But all of these, I really encourage people to follow up and look up exactly, because they provide a lot of the technical details behind what I'm mentioning here. And thank you.
We have time for a few questions. If people just want to raise a hand, I'll bring you the mic. Anybody? No questions? Okay. Thank you very much, Yakov.